This asteroid is doing something that shouldn't be possible. There's a photograph taken by a spacecraft that watches the sun for a living that should not show what it shows. The spacecraft is called SOHO, the Solar and Heliospheric Observatory, and its job is to stare at our star day after day, watching for flares and storms of charged particles. But buried in its archive, and in the archive of a second spacecraft called Stereo, there's something else. A small point of light, swinging in close to the sun, closer than any other named object in the solar system ever gets, and trailing behind it, faint as a held breath, a tail. Tails are not supposed to be a mystery. We solved that problem a long time ago. A tail means ice. It means a comet, a dirty snowball drifting in from the cold edges of the solar system, warming as it falls toward the sun until the ice on its surface turns straight to gas and drags dust out with it. And that gas and dust, pushed by sunlight and the solar wind, stream away into a tail that can stretch for millions of kilometers. That is the deal. Ice makes tails. Rock does not. The object in those SOHO and Stereo images is not ice. It is rock. A blue, sun-baked, roughly 5.5 to 6 kilometer wide chunk of carbon-rich stone named 3200 Phaethon, and by every rule we have written about how solar system objects are supposed to behave, it has no business growing a tail at all. And yet it does. Every single time it swings in toward the sun, it does it again. This is the story of an asteroid that keeps breaking its own rulebook, of the scientists who spent the better part of 2 decades trying to figure out why, of the answer they finally found in 2023, of the deeper argument that answer immediately opened up and still is not closed, and of a spacecraft now waiting on a launch pad in Japan that hopes to fly close enough to Phaethon to finally watch it happen. Phaethon was found in 1983, and the way it was found matters because it was the first asteroid ever discovered from space rather than from the ground. The instrument that caught it was called IRAS, the Infrared Astronomical Satellite, a joint mission of the United States, the Netherlands, and the United Kingdom that spent 10 months scanning the entire sky in infrared light, cataloging everything from newborn stars to distant galaxies. Sifting through that flood of data, astronomers found a small, fast-moving heat signature that did not match anything already known. They named it Phaethon, after the son of the sun god Helios in Greek mythology, the boy who begged to drive his father's sun chariot for one single day, lost control of the horses, and scorched the earth before Zeus struck him down to stop the damage. It is, in hindsight, an almost unfair amount of foreshadowing to load onto a name, because Phaethon, the asteroid, spends its entire existence doing something close to what the myth describes. Most asteroids orbit out in the main belt, between Mars and Jupiter, a comfortable few 100 million kilometers from the sun's worst temper. Phaethon does not live there. It belongs to a family of asteroids called Apollo asteroids, whose orbits cross Earth's, and its path around the sun is a long, stretched ellipse that carries it from out past the orbit of Mars all the way down to a perihelion, a closest approach of about 0.14 astronomical units. That is roughly 21 million kilometers, which sounds like a great deal until you set it beside Mercury, the innermost planet, which never gets closer to the sun than about 46 million kilometers at its own perihelion. Phaethon dives inside Mercury's orbit. Of every asteroid we have ever given a name to, none goes closer to the sun than this one. At that distance, the sun does not simply warm Phaethon's surface. It cooks it. Models of Phaethon's close approaches put its surface temperature at somewhere around 730 degrees Celsius, hot enough to melt lead, hot enough to soften some kinds of glass, hot enough that anything icy sitting anywhere near that surface would have boiled away in the earliest days of the solar system and never come back. Ice cannot survive a single one of Phaethon's orbits, let alone the billions of years it has presumably been making this same suicidal loop past the sun. So when observers first noticed, decades ago, that Phaethon brightens and grows a faint tail every time it comes in close, the obvious explanation was off the table before anyone could even reach for it. There is a second oddity sitting right on the surface of the problem, literally, and that is color. Most asteroids are a fairly unglamorous gray or a dull reddish-brown. Phaethon is blue. Not blue in the poetic sense, blue in the spectral, measurable sense, the kind of color that gets an object sorted into a specific bin by the astronomers who classify these things. Phaethon is what is called a B-type asteroid, a rare carbonaceous subclass, rich in carbon compounds, and only a small fraction of known asteroids fall into that category at all. Blue asteroids are already the odd ones out of the party. A blue asteroid that also happens to be the closest sun grazer of them all, and that also happens to grow a tail like a comet, was never going to sit quietly in the background of the catalog. For most of the time astronomers have known about Phaethon, they have not actually seen it. They have seen a point of light, a smear of reflected sunlight moving against the stars, and everything they knew about its size and shape had to be inferred from how that point brightened and dimmed as it turned. That changed in December of 2017, when Phaethon came closer to Earth than it had in decades, passing within about 10,300,000 kilometers of us, roughly 27 times the distance between the Earth and the Moon. By the standards of the solar system, that is practically leaning over the fence. In the Arecibo Observatory in Puerto Rico, its enormous dish, only recently patched back together after hurricane damage, pointed its planetary radar at the asteroid and started pinging it. Radar does not care about sunlight. It sends a pulse of radio energy out, waits for the echo, and builds a picture out of what comes back, which means that for the first time, anyone was going to get something close to an actual image of Phaethon's surface rather than a mathematical guess about it. The images that came back had a resolution of about 75 meters per pixel, and what they showed was a body more than 6 kilometers across at the equator, roughly spheroidal, close to a slightly squash ball. Not a jagged potato of the kind many asteroids turn out to be, but something rounder, smoother, more finished looking. It was not featureless. Near the equator, the radar picked out a large concavity, a depression at least several hundred meters across, a scoop taken out of the side of the world. There was a possible crater more than a kilometer wide, sitting below 30 degrees of latitude. And near one of the poles, there was a conspicuous dark circular patch, about 600 meters across, dark in the specific sense that it reflected radar poorly, which usually means the surface there is different somehow, smoother or dusty, or built from something that does not bounce radio waves the way the rest of it does. None of that answers why Phaethon grows a tail. But it is the difference between arguing about a rumor and arguing about a photograph. From December of 2017 onward, the object at the center of this mystery stopped being an abstraction and became a place, with a shape and a scar near its equator, and a dark stain near its pole that nobody has explained either. For a long time, the working assumption was that Phaethon's tail must be made of dust, and that assumption did not come from nowhere. It came from a real observation, made in 2009 and published the following year by two astronomers, David Jewett and Jing Li, who did something nobody had thought to do before. They went looking for Phaethon in the images of a spacecraft that was not built to look at asteroids at all. The spacecraft was stereo, and its coronagraph is designed to blot out the disk of the sun so that the faint corona around it becomes visible. That makes it a superb instrument for catching something small and dim passing very close to the sun, which is precisely the one place on Phaethon's orbit where a ground telescope can never follow it. And when Jewett and Lee pulled up the frames from Phaethon's perihelion passage, they found that the asteroid had done something abrupt. It had brightened. Not gradually, not by a little, but by a factor of two, suddenly, right at its closest approach. Something had come off it, a cloud of solid grains, released at the moment of maximum heat. Jewett and Lee argued that no ice was needed to explain it, and they were right about that much. At roughly 1000 Kelvin, which is around 727 degrees Celsius, a surface will crack simply because it is being heated and cooled that violently, the way a hot glass cracks when you run under a cold tap. Rock that contains water bound into its mineral structure will dry out, shrink, and split. That process, thermal fracture and desiccation cracking, needs no comet, no snowball, no ice at all. It just needs heat and repetition, and Phaethon has both. Out of that paper came a phrase that stuck to Phaethon permanently, and that you will still see attached to it in almost every article written about it since. A rock comet. An object that behaves like a comet without being one, that sheds material near the sun for reasons that have nothing to do with the physics that makes comets shed. It was a good name, and it was, as far as it went, a good explanation. But an explanation is a promise, and Jewett and Lee's had a number attached to it that nobody could ignore. We will come back to that number, and when we do, it will take the entire tidy picture apart. First, though, the tale itself, because reasonable is not the same as tested, and eventually a team of researchers decided to actually test it. The team was led by an astronomer named Qiqing Zhang, and the tool they used was patience. Spacecraft like SOHO and Stereo have been staring at the region around the sun for decades, mostly hunting for solar storms, and in doing so they have incidentally photographed Phaethon dozens of times as it made its close approaches. Zhang and his colleagues went back through that entire archive, digging through images going back to the 1990s, looking specifically at how Phaethon's brightness and tail behaved across many different orbits, not just one flashy appearance. Comets, when they glow near the sun, often do it partly through a very specific process, sodium atoms in their material getting excited by sunlight and emitting a distinctive glow, a phenomenon well documented in sun-grazing comets for years. An earlier line of research had floated the idea that the same thing might be happening to Phaethon, that the ferocious heat of perihelion might be enough to vaporize sodium locked inside the asteroid's rock and vent it into space, even with no ice anywhere in the picture. Sodium melts and boils at temperatures far lower than most of the silicate minerals that make up an asteroid structure. It does not need 730 degrees Celsius to vaporize. It needs far less than that, which means sodium sitting inside a rock that gets baked to those temperatures at every close pass has every opportunity in the world to boil straight out of the surface and into space without a single molecule of ice ever being involved. When Zhang's team ran the numbers against the archival images, the pattern held. They found Phaethon's tail present across 18 separate close solar approaches spanning the years from 1997 to 2022, and the behavior of that tail matched what sodium emission should look like far better than it matched ordinary dust. The 2023 study, published in the Astronomical Journal, confirmed it. The tail is not vaporized ice because there is no ice. It is also not, primarily, the kind of dust tail you'd see streaming off a classic comet. It is sodium boiled directly out of the rock by solar heat and glowing as it escapes, an entirely different physical process producing something that, from a distance, looks enough like a comet's tail to have confused observers for years. That is worth sitting with for a moment, because it is a genuinely strange thing for a solid rock to do. Picture a stone left out in a furnace hot enough to soften glass. And picture that stone, every single time it goes into the furnace, breathing out a faint golden vapor that a telescope 150 million kilometers away can detect and photograph. That is what Phaethon has apparently been doing for as long as anyone has been able to check. and probably for a great deal longer than that. So the tail itself, as of 2023, is settled. It is sodium gas, not classical cometary dust. National Geographic's framing of this discovery captured the core paradox well, that because Phaethon is rocky and not icy, this tail should not exist at all, and that the resolution turned out to be sodium doing a job normally reserved for ice. That much of a story has an answer. What does not have an answer, or rather what has three overlapping, competing answers currently being argued about in the scientific literature, is the deeper question sitting underneath the sodium. Where precisely inside Phaethon's rock is that sodium coming from? What exact chemical process is releasing it, and why, after what is presumably billions of years of repeated 730-degree roastings, has Phaethon not simply run out of whatever it is that keeps producing this activity? A rock that has been baked at those temperatures every single orbit for that long should, by any simple accounting, have exhausted its volatile material long ago. It has not. Figuring out why has turned into one of the more interesting open arguments in small body science. The next major piece of the puzzle came later in 2023 from a team led by Michael Granvik and a colleague named McLennan, published in Nature Astronomy. Rather than watching Phaethon's tail from a distance, they went back to its infrared spectrum, essentially the fingerprint of light that Phaethon's surface reflects and emits, and compared it very carefully against samples of actual meteorites that have fallen to Earth. What they found was a striking match to a specific and extremely rare class of meteorite called CY carbonaceous chondrites. As of that study, only 6 specimens of this meteorite type were known to exist anywhere on Earth. CY chondrites are notable for having been altered by heat and water early in their history, leaving behind a mineral structure that is unusually prone to further chemical breakdown when heated again. This gave the sodium story a home. If Phaethon's surface really is built from something like CY chondrite material, then repeated heating at perihelion would not just cook sodium out of simple salt-like minerals, it would also drive a broader process called thermal decomposition, where heat itself breaks down mineral structures and releases trapped gases along with small grains of dust and gravel. The Granvik and McLennan team put the two pieces together directly, proposing that sodium emission explains the faint glowing tail seen near the sun, while thermal decomposition of this specific chondrite-like material explains how Phaethon also sheds actual solid debris, the dust and pebble-sized fragments that do not just glow and disperse, but that could, over time, seed a stream of meteoroids trailing along Phaethon's orbit. That second half of the finding mattered enormously, because it was the first time a physical mechanism had been proposed that could plausibly connect Phaethon's perihelion baking to something Earth actually experiences directly, which we will come back to shortly. For a while, this looked like it might be close to the full picture. Sodium venting for the visible tail, thermal decomposition of a rare, water-altered chondrite material for the solid debris. 2 mechanisms, one asteroid, tidy story. Then in 2024, a different team, publishing in Nature Communications, pointed at a real problem with that tidy story and did not let it go. Their objection was straightforward. If Phaethon really is made of something like CY chondrite material, heavily altered and thermally fragile, and if it really has been enduring these same 730-degree perihelion passes for a very long stretch of its history, then its surface volatile should have been cooked out and exhausted long ago, the same way a pot left on a stove eventually boils dry. Phaethon has clearly not gone dry. It is still producing activity, decade after decade, orbit after orbit, with no sign of slowing. So either the timeline is wrong, or the composition model is wrong, or something about the mechanism itself is more resilient than the CY chondrite picture allows. This second team's answer came out of the laboratory rather than the telescope. Instead of using Cy chondrite material, they worked with a different, somewhat more common class called Cm chondrites, which also contain clay minerals and volatile compounds, but have a different structural history. They took fragments of these meteorites and subjected them to rapid, repeated heating cycles in a lab, deliberately designed to mimic the fast heating rate Phaethon experiences as it swings past the sun and then swings away again just as quickly. Heating rates on the order of a few degrees Celsius per minute, applied over and over in a cycle rather than as one single bake. What they found was that this specific combination, fast cyclic heating combined with the low permeability of the rock, meaning gas has a hard time escaping quickly through the material, actually causes reactions between escaping volatile gases and the minerals that are decomposing around them. In particular, sulfur-bearing gas released during heating gets partly trapped within the rock rather than escaping cleanly, and that trapped gas appears to protect certain iron sulfide minerals from being fully broken down during each heating cycle. The practical effect is that the material does not exhaust itself the way a simple one-shot heating model would predict. It survives repeated roasting far better than expected because the very gases it is releasing are, in a sense, shielding part of its own volatile reservoir for being used up too quickly. So now there are two serious, published, laboratory and observation-backed explanations circulating for how Phaethon manages to keep doing this without running dry, and they do not agree on the starting material. One camp says the surface spectrum points to Cy chondrite composition and thermal decomposition of that specific mineral suite. The other camp says the survival puzzle only makes sense if the material behaves like Cm chondrite, with a self-protecting sulfide chemistry that keeps producing gas cycle after cycle. Both camps agree that sodium venting is very likely part of what produces the visible tail. Neither camp has convinced the other on everything else. This is, as of the most recent research on the subject, still an open and active argument, not a settled matter with a tidy textbook answer. If there is one honest sentence to describe where the science currently stands, it is this: we know what the tail is made of, and we're still arguing about exactly what is happening inside the rock to keep making it. As if that were not enough mystery for one 5.5-kilometer object, Phaethon has a second, entirely separate strange behavior that nobody has managed to explain at all. Its rotation is speeding up. A study published in 2022 combed through 32 years of observational data on Phaethon, spanning thousands of individual rotations, essentially thousands of separate measurements of how fast the asteroid spins on its axis. Across that long baseline, the researchers found that Phaethon's rotation period, the length of its day, is decreasing by about 4 milliseconds every year. 4 milliseconds sounds trivial, and on a human timescale it is, but for a solid 5.5-kilometer body drifting through the vacuum of space, a measurable, consistent accelerating spin rate is not something that happens by accident. Something is acting on Phaethon steadily, year after year, nudging its spin just a little bit faster each time, and 32 years of careful data collection was enough to catch it happening. There is, right now, no confirmed explanation for why this is occurring. The leading speculative idea on the table is that it might be connected to the same comet-like activity driving the sodium tail, the idea being that material venting off an irregularly shaped, rotating body in a particular pattern could act like a very slow, very gentle thruster, gradually torquing the spin rate over time. The same basic principle that causes comet nuclei to sometimes tumble or change their spin as they outgas unevenly. If that turns out to be correct, it would be the first confirmed case of an object generally classified as an asteroid demonstrating comet-like outgassing forces strong enough to physically alter its own rotation. That would be a genuinely significant result. But it is important to be honest about where this currently sits in the science. It is a hypothesis, a reasonable one, offered by researchers who know they do not yet have direct proof, not a confirmed mechanism. The spin-up is real and well measured. The cause is still speculation. 2 open mysteries about the same asteroid would already be a lot. There is a third, and it might be the biggest one, because it connects Phaethon directly to something almost everyone watching this has probably seen with their own eyes without knowing anything about where it came from. Every year, in the middle of December, Earth passes through a wide stream of debris scattered along Phaethon's orbital path, and the result is the Geminid meteor shower, reliably one of the strongest and most reliable meteor showers of the entire year. Under good conditions, away from city lights, with a clear dark sky, the Geminids can produce somewhere between 120 and 160 meteors per hour at their peak, typically falling in the 2 to 3 o'clock in the morning window on the peak night, which lands around December 13th and 14th each year. Bright, fast, often colorful streaks, more numerous and more dependable than almost any other annual shower. And every one of them is a tiny fragment of debris, in most cases smaller than a grain of sand, burning up in Earth's atmosphere after having spent who knows how long drifting along Phaethon's orbital track. This is already unusual on its own, because most major meteor showers trace back to comets. The Perseids, one of the most famous showers of the year, come from debris shed by Comet Swift-Tuttle. The Orionids and the Eta Aquariids trace back to Halley's Comet. Comets are, in general, the expected source of meteor showers, because comets are the objects we understand to shed large amounts of ice and dust as they warm near the sun. The Geminids, along with one other shower called the Quadrantids, are the rare exceptions. Both of them trace back not to comets, but to rocky asteroids, Phaethon in the case of the Geminids. That alone made Phaethon interesting long before anyone confirmed its sodium tail. It meant that somehow, somewhere, at some point, Phaethon had produced an enormous quantity of debris using a mechanism that had nothing to do with the classic icy sublimation that seeds every other major shower. And this is where the story runs into its biggest unanswered question of all, bigger even than the chemistry argument over Cy versus Cm chondrite material, because it is not a question of mechanism, it is a question of scale. The Geminid stream is not a light dusting. Estimates of its total mass, the combined weight of every particle scattered along that orbital path, run to levels that in some calculations approach a mass comparable to Phaethon itself. Thermal modeling of how much ice Phaethon could plausibly retain, even the most generous estimates, suggests there simply is not enough frozen material inside it to have produced that kind of sublimation-driven ejection, the way a genuine icy comet nucleus might. Even a small trapped ice reservoir would only produce weak, gradual sublimation, nowhere near forceful enough to blast out a debris stream on the scale the Geminids appear to represent. Here is the number, and it is worth saying slowly, because the size of the gap is the whole problem. The dust cloud Jewett and Lee watched come off Phaethon at perihelion, the one that made it brighten by a factor of 2, has been estimated at roughly 300,000 kilograms of material. 300 tons. That is a lot of gravel to throw off a rock in one afternoon, and it sounds like a great deal until you set it against what has to be explained. The Geminid stream, the debris field Earth plows through every December, has been estimated at something on the order of 1 trillion kilograms. 1,000 billion. A million. Divide one into the other, and you get the shape of the difficulty. Phaethon would need to do what it did in 2009 something like 3 million times over to build the stream we actually fly through every year. 3 million perihelion passes, at roughly 1.5 years apiece, is somewhere in the region of 5 million years of continuous, uninterrupted shedding at exactly the rate we happen to catch it at, with nothing lost, nothing dispersed, Nothing swept away by the sunlight and the solar wind and the gravity of the planets over all that time. The Geminid Stream is not 5 million years old. Most estimates put it at 1,000 years, perhaps a few thousand. It is astonishingly young, which is part of why it is still so dense and so reliable. So the arithmetic does not merely fail to work. It fails by a margin so wide that no amount of tuning the assumptions can rescue it. Whatever Phaethon is doing today, patiently venting sodium and cracking off grains at every close pass, it is not what built the Geminids. The activity we can actually observe is a trickle, and the stream is a flood. We are watching the wrong event. That single mismatch is the reason the breakup hypothesis exists at all. Not because anyone particularly wanted to invent a violent ancient catastrophe, but because the gentle explanation, the one we can see happening with our own instruments, comes up 3 million times short. One proposal, put forward in dynamical modeling published in 2024, suggests the Geminid Stream was not built up slowly, orbit after orbit, through the kind of gradual perihelion shedding the sodium and thermal decomposition studies describe. Instead, this model proposes a single dramatic event, a rotational breakup, roughly a couple thousand years ago, in which Phaethon, already spinning dangerously fast and already weakened by repeated solar heating, partially fractured or shed a substantial piece of itself all at once, flinging out the bulk of the material that now makes up the Geminid Stream in one comparatively brief catastrophic episode, rather than through millennia of quiet leakage. That is a compelling picture, but it is far from a settled one, and part of the reason it is hard to settle comes down to something almost embarrassingly basic: how you count the debris in the first place. The estimated total mass of the Geminid Stream changes dramatically depending on where researchers set the lower size cutoff for what counts as a stream particle. If the smallest particles counted are relatively large, comparable to a grain of sand, the total estimated mass comes out one way. If the size cutoff is pushed down to particles as small as 1,000th of a millimeter across, genuinely microscopic dust, the total estimated mass of the stream can increase by 7 orders of magnitude. 7 orders of magnitude is not a rounding difference. It is the gap between a small number and that same number followed by 7 more zeros. Different reasonable choices about where to stop counting produce wildly different pictures of how much material we are even trying to explain the origin of. So the honest state of affairs right now is this. We know the Geminids come from Phaethon. We know Phaethon is rocky, essentially ice-free, and that classic cometary ice sublimation cannot plausibly account for a debris stream of the size the Geminids appear to represent. We have at least 2 candidate mechanisms, sodium venting and thermal decomposition of some chondrite-like mineral suite, that can explain ongoing, gradual, present-day shedding of material. We have a competing proposal that the bulk of the stream's mass actually came from one ancient, sudden, catastrophic breakup event rather than slow accumulation. And we do not have an agreed number for how much mass we are actually trying to account for in the first place, because that number depends on a definitional choice about particle size that different researchers have made differently. This is not a case of scientists disagreeing over minor details around a settled answer. This is a genuinely open question, sitting right at the center of one of the most famous, most reliably observed meteor showers of the year, and it remains unresolved. It is worth pausing here to notice what an unusual position that puts Phaethon in. This is not some faint, forgotten rock buried deep in the outer catalog of minor planets. It was the first asteroid ever discovered from space. It is the closest approaching named asteroid to the Sun that we know of. It produces one of the most reliable and impressive meteor showers visible from Earth every single December. Its rotation is measurably, mysteriously accelerating. Its tail defies the basic textbook rule separating asteroids from comets. And after 4 decades of study, with modern spacecraft, laboratory simulations, and archival data spanning 30 years, we still cannot say with certainty exactly what it is made of, exactly why its activity persists without running dry, or exactly how it built the debris field that lights up our December skies. Phaethon has been sitting in plain sight, repeatedly observed, repeatedly measured, and it is still keeping secrets, which is exactly why a spacecraft is being built to go and look at it directly. The mission is called Destiny Plus, an acronym standing for Demonstration and Experiment of Space Technology for Interplanetary Voyage, Phaethon Flyby, and Dust Science, developed by Japan's space agency, JAXA. Its entire purpose, once it reaches its target, is to fly directly past Phaethon at close range and do the things no telescope on Earth or in orbit can do from tens of millions of kilometers away, actually image the surface in detail, and directly sample the dust environment surrounding the asteroid as it passes through. The plan calls for Destiny Plus to come within about 500 kilometers of Phaethon's surface during its closest approach, using a multi-band telescopic camera to map surface features and composition in detail, information that could finally settle the argument over what kind of chondrite-like material Phaethon is actually built from, CY, CM, or something else entirely. Alongside the camera, the spacecraft carries an instrument called the Destiny Dust Analyzer, built by the German Aerospace Center, DLR, specifically designed to capture and analyze individual dust particles as the spacecraft flies through Phaethon's surrounding debris environment. That instrument is the one most directly aimed at the Geminid mystery, because it will be sampling, essentially in real time, the same kind of material that ultimately falls to Earth as December meteors, examined up close rather than inferred from a streak of light in the atmosphere. As something of a bonus, current mission planning also has Destiny Plus flying past the second, smaller asteroid on its way to Phaethon, an object designated 155140, 2005 UD, giving the mission 2 targets rather than 1 before its main encounter. Here's where the story gets complicated in a very ordinary, very human way, because this mission has had a rough road just getting off the ground, literally. Destiny Plus was originally planned to launch using a new Japanese rocket called Epsilon-S, an upgraded version of Japan's solid-fuel Epsilon launch vehicle. In July of 2023, during a ground test of that rocket's second-stage engine, the engine exploded. Nobody was hurt, but the damage went well beyond the loss of a single test article. The explosion destroyed the vacuum combustion test facility at the Noshiro Rocket Testing Center, the very facility JAXA needed in order to continue developing and testing that engine. Reconstruction of that facility is not expected to be complete until Japan's fiscal year 2027 at the earliest. That is not a delay measured in months. That is years of testing infrastructure that simply no longer existed. Faced with that reality, JAXA made the call to abandon the Epsilon-S rocket for this mission entirely and switch Destiny Plus onto a different, already flying launch vehicle, the H-3 rocket, Japan's newer flagship rocket family. That switch pushed the spacecraft's launch date out to 2028, a delay stacked on top of an earlier delay the mission had already absorbed back in 2023, when Epsilon-S problems first became apparent and pushed the original launch target into 2025. There is genuinely good news buried inside this frustrating chain of setbacks. JAXA has stated clearly that even with the launch pushed to 2028, the timing of the actual flyby of Phaethon itself remains unchanged, still targeted for Japan's fiscal year 2030, which runs roughly from April of that year through March of the following year. In other words, the years lost to the rocket failure are being made up somewhere in the mission's interplanetary cruise phase through a different trajectory design, rather than costing the mission its actual encounter with Phaethon. According to JAXA, there is no expected impact on the mission's scientific objectives. The rocket changed. The path changed. The appointment with the asteroid did not. Destiny Plus will not be flying alone when it finally does launch. Its ride on the H-3 rocket is expected to be shared with an entirely separate mission belonging to the European Space Agency, called Ramses, headed toward a completely different and equally famous near-Earth asteroid, Apophis. That shared H-3 launch is currently expected in April of 2028, riding the same general timeline that pushed Destiny Plus off its original rocket. Two space agencies, two different asteroids, one shared rocket, a reminder that even missions built around wildly different scientific targets sometimes end up quite literally sharing the ride to get off the planet. None of this is unusual in the world of interplanetary missions, where rocket failures, facility damage, and multi-year schedule shifts are simply part of the cost of doing business. When you're trying to leave Earth's atmosphere entirely, what matters for Phaethon is that the appointment is still on the books. Sometime in Japan's fiscal year 2030, a spacecraft built specifically to answer the questions this asteroid has been asking for 4 decades will fly within 500 kilometers of its surface, camera running, dust analyzer open, ready to catch whatever Phaethon happens to be doing at that particular moment in its endless loop past the sun. It is worth remembering, standing at the end of all this, just how strange the basic premise still is, even after everything we now know. A 5.5-kilometer chunk of blue, carbon-rich rock, discovered by accident in a satellite built to map heat across the entire sky, spends its entire existence looping in from the outer solar system, diving in past the orbit of Mercury itself, close enough to the sun that its surface reaches temperatures that would melt lead, and then racing back out again, only to repeat the entire dive a little over a year later. Every single time it makes that closest approach, something happens to it that, by every rule written for objects like it, should not happen at all. Sodium boils directly out of its rock and forms a faint glowing tail, visible to spacecraft built to watch the sun, not to watch asteroids. And somewhere in that same repeated cycle of violent heating, enough solid material has been shed, across some combination of gradual leakage and possibly one ancient violent breakup, to seed a stream of debris that Earth plows through every December, lighting up dark skies with 100 meteors an hour or more, a fireworks display older than most of human civilization, produced by a process we still cannot fully explain. We have solved one layer of the mystery. The tail is real, and it is sodium, confirmed through years of patient archival digging by researchers willing to look at old spacecraft data with new questions. That answer is not new, and is not really in dispute anymore. But underneath that answer sit at least 3 more, each one still being argued over in the pages of active scientific journals, each one backed by real laboratory work and real observational data, and none of them fully agreed upon. What exact mineral makeup allows Phaethon to keep producing this activity without ever running dry? Why its spin is measurably speeding up year after year in a way that might be the asteroid quietly propelling its own rotation through the very activity that puzzles us in the first place? And where exactly the bulk of the material feeding one of the sky's most reliable meteor showers actually came from, whether it leaked out slowly across thousands of years or was blasted free all at once in a single violent moment we happen to just barely miss witnessing. Somewhere around the year 2030, if the schedule holds this time, a small robotic spacecraft is going to fly close enough to answer at least some of these questions directly, close enough to see the surface itself rather than infer it from a smear of reflected sunlight 93 million miles away. Until then, Phaethon will keep doing exactly what it has been doing for as long as anyone has been watching. It will dive in past Mercury's orbit. It will bake at temperatures that would soften stone. It will breathe out its faint sodium glow into the dark, and it will pull away again, unharmed, unchanged, carrying its secrets back out into the cold, waiting for the next December and the next arrival of light in our sky that most people watching it will never think to ask where it came from.